Dear all, my name is Sahil Sharma. In this video, I am going to cover the introduction to ARM programming. Along with that, we will be doing some coding for addition and subtraction of two 32-bit numbers. First, the introduction to ARM programming will be discussed. Then why we need ARM programming, assembly directives that are used in ARM programming will be covered, the registers that are available to us in ARM programming. Then by using Keel Microvision software, we will see how to open a new project and then adding our program in the project. Then I will be discussing three types of addition and subtraction. First type will be direct addressing mode, second type will be indirect addressing mode, third type will be using barrel shifter. During indirect addressing mode, we will need some values to be edited at some memory location. I will tell you how to do that. Then I will show you the whole code for addition and subtraction with all the methods included in it. Then we will do some coding and implementation part on the Keel Microvision software. ARM is Advanced RISC Machine. ARM7 is a 32-bit RISC processor architecture developed by ARM Corporation. ARM instruction set has following features. We can use load and store architecture. 32-bit instructions are available. For data, we have three options: 8-bit data, 16-bit data, and 32-bit data. There are 32-bit addresses. Total of 37 registers are there, out of which 30 are general purpose register with 15 out of them as visible to us. 6 out of 37 are status registers, and 1 we have the program counter. Why do we need ARM programming? In older computers, address bus was 16-bit wide. Such microprocessors had a limitation of addressing up to 2^16 memory locations. But ARM processors have a 32-bit wide address bus. So ARM processor can address up to 2^32 memory locations. Earlier we had 8-bit wide data bus in the old computers, but ARM has a 32-bit wide data bus. So each location is a word which is of 4 bytes. For an ARM processor, the addressable capacity is 2^32 bytes. So total of 4 gigabytes of memory can be addressed. What are assembly directives? The directives allocate the space and in many cases define different types. Assembly directives are not instructions. So let's see what does these keywords mean. Area helps us in making a new block of data or code. There are two types of area which can be defined in our code. One is the block of data, the other area is the block of code. Entry: declare an entry point where the program execution starts. When the program execution starts, entry is the keyword which is searched for starting of execution. Align: align directive aligns the data or code to a particular memory boundary. DCB allocates one or more bytes of data. DCW allocates one or more half words of data. DCD allocates one or more words of 32 bits of data. Space directive is used for allocating 0 values in the block of memory with a particular size. Fill directive is used for allocating a block of memory and fill with a given value. EQU and RN. EQU gives a symbol name to the numeric constant. RN gives a symbol name to a register. Export and import. Export declares a symbol and make it referable by other source files. Import provides a symbol defined outside the current source file. Include /get. It helps in including a separate source file within the current source file. Proc declares the start of a procedure. Endp designate the end of a procedure. End designate the end of a source file. So these are the registers usable in ARM programming. There are 15 visible 32-bit general purpose registers. R0 to R14. R0 to R12 are the registers which can be used by the programmer by giving some values. SP is the stack pointer. LR R14 is the link register. LR link register holds the return address of a subroutine. PC. Program counter is not considered as a general purpose register. The program counter holds the next instruction to be executed. CPSR, current program status register. CPSR holds application program status register flags, the current processor mode, interrupt disable flags, current procedure state, endianness state. Endianness state may be big endian, little endian. Execution state bits for the IT block. SPSR. SPSR means saved program status register. The SPSR is used to store the current value of the CPSR when an exception is taken so that it can be restored after handling the exception. So when some exception occurs, the current value of CPSR goes into SPSR and it can be called back after the exception has been handled. When you want to open a new project with the legacy device database, the steps are as follows. Initially when you open the Microvision software, it will look something like this. You have to click on project, then new Vision project, because we want to add a new project. In the default folder, we can save the project with any name, so I have kept the project name as ARM and then click. After we click save, we will be asked which device we want to use. So I have selected legacy device database. Then we have to select the ARM 7 big endian, then click OK. In the project tab, we can see that project name is ARM. Target 1 and source group are the blank folders. So we have created our new project. After the project has been created, now we want to add a program in our project. Suppose we have saved our program with the name add subdirect indirect .asm. .asm and .s both are valid extension names of the ARM program. ASM means assembly. In order to add a program in the project, you would have to double click this source group 1 part. After double clicking, you will be taken here. So at this place you have to select the program whichever you want to import. After clicking the program name, we will click add button. So adding this takes us here. In the source group 1, we have got our program imported. So this is how we add a program in our project. Now I am going to discuss the first technique to do addition and subtraction. The technique is by using direct addressing. So what does direct addressing mode means? To justify the direct addressing mode, the values of registers R1 and R2 are directly used for the purpose of addition and subtraction. So we have two blocks here. The first block is the area code and the second block here is area data. Now the indentation matters here. So you would see that the space is constant at these places. So this is known as indentation. And all the labels here, entry is a label, S is a label, value 1 is a label, value 2 is a label. So the entry directive is the starting point of the execution of program. In the data section, there are two values. Value 1 is a DCD value. So DCD allocates us 32 bits of word. So this is a 32-bit value which has been given to value 1, and this is a 32-bit value which has been given to value 2. In the code section, this statement LDR R1, value 1 means that we have given R1 a value of 90H, and R2 we have a given value of 94H. When we say add R3, R1, R2, this means so the addition will take place. As this is a hexadecimal addition, 9 plus 9 means 18. It can be written as 12 in hexadecimal form. So the answer of addition is 124H. And for subtraction, carry will be taken by the 0, so this will become 16. 16 minus 4 is 12, so 12 can be written as C in hexadecimal, and this will be left with 8, so even this will be needing some borrow, so that this part will become 16 plus 8, which is 24. 24 minus 9 is 15, which means F, and all the corresponding values will become F, because this number was so the answer is so this is how direct addressing mode addition and subtraction works. For indirect addressing mode, there are two sections, code and data. At entry point, the execution starts, and from data section, value 1 and value 2 holds the same value as in direct addressing mode, 90 and 94. So here we want to first initialize R1 with value 1. So R1 holds 0090H. R2 holds 94H. Now to justify indirect addressing mode, the values of R5 and R6 are given values indirectly by traveling to memory location R1 and R2. This means that suppose there is some memory location. So these are the 8 places here. So when we say we have a value at 90H location, which means that I want to use R1 as a memory location. So this memory location will hold 4 bytes of data, and these 4 bytes will be stored here. So suppose I have value of 10 here, and at 94H location, that is R2, I have value 20. So these values will be used for addition purpose. So R7 will become 10 plus 20H, which means 30H, and R8 will become 10 minus 20H. So 10 minus 20H means the answer will be well, here we saw that I took 4 bytes of value at 90H as 10, and here we saw I took value of 20 at 94H. Now we should learn how to do this in our memory. So how to edit value at a memory location. So when you have saved your program, click on build. This build will check for the errors. So if there are no errors, then we can click on the start and stop debug session button. So when we click this debug session button, it will ask for the evaluation mode with a code size limit of 32K. You have to click OK. When you enter the debug mode, click on debug in the toolbar section and click memory map. So initially you will be shown with these locations. These currently mapped memory locations have execution and read permission. So now we want to add some map range here according to our memory which we want to use. So the memory location I want to edit was 90H and 94H. So it will come under this memory location range 0x00000 and 0x100000. So 00090 and 00094H will come between this range. So I want to give the read permission, write permission and execute permission. After clicking the map range button, you will see that these permissions have been updated and our values have been changed from in the current map section. After that, click close, and now we want to view our memory window. So I have taken memory 2 window, and in memory 2 initially my memory 2 window will be empty. I have to search for 0x90. So in the 0x so after searching for 0x90, these 4 values will be there. So the first value is the 87th byte, second value is the 88th byte, and similarly we will reach 90th byte. So if I want to update some value at 00000090H, then I have to change value in these 4 bytes. So I have changed here in the step 10 that 90H holds 10H and 94H holds 20H. Okay. Now the third technique, addition and subtraction using barrel shifter. So there are two sections, code and data. Barrel shifter means that we want to use these commands: LSR logical shift right or LSL logical shift left. So what happens is, we have R1 with value of 90, we have R2 with value of 94H. When we write move statement R9, R1, LSR1, which means we have to logically shift right the value of R1 by location of 1 bit, and then the answer will be shifted to R9. So this means 90H is 1001 0000. Want to right shift the value of R1 by 1 location. This means the answer will be 01001000. So this is 4, this is 8. So my R9 will hold 48H, and in case of R10, the R2 value has to be logically shift left by 1 location. So my R2 is initially 94, logically shift left by 1 location. It means the value will be 128. So when we add R9 and R10 and save value in R11, R11 will hold value of by using hexadecimal addition. R11 will hold 170H, and similarly for subtraction, sixteen will come. 16 minus 1 is 15, so the answer will be R12 equal to this. So the combined code for addition and subtraction will be written like this. In the code section, all the values for direct addressing, indirect addressing, and parallel shifter will be calculated. SBS is a technique to end the program. S is a label, so at line 23 branching will occur to S location, which is same as location 23. So this line will continue forever, which means end of the program. And data section is given the value of 90 and 94 in value 1 and value 2. Now let's do some coding and implementation demo. Now I am going to continue the implementation part. I have written the program and I have already added this program in the project arm. So initially I will be doing the compilation by using build. You can see that 0 error and 0 warning is there, so we will continue by debugging. Debugging can also be done by debug tab, start and stop debug session, evaluation mode, okay. So I have already opened memory 2 tab at this place, and I want to give the permission first at location 90 and 94H, because I know that I will be editing some value for the interact mode. So let's give the permission at location 90 and 94. Go to memory map. After entering the range, read, write, execute permission and map range. So the value in the current map has been updated. Close. So now I have the permission to edit value at location 90H. So I will update value here 10, and for 94 I will be updating value at 94th location 20. Now let's run this program line by line. You can do it from here also using F11. So when I click this, you will see that first line has been executed and our program counter has reached here. So R1 has value 1. Value 1 is 90. So you can see in the register section that R1 has 90 now. executing next line. R2 has 94. Addition result is 124. Subtraction result is FFFFFC. Now then indirect addressing. R5 has value 10, which we updated in the memory section. R6 has value 20. We had updated at 94th location, value was given as 20. Addition is 30. Subtraction is FFFFFF0. Now when we execute the next line, we will be executing next 4 lines for barrel shifter mode. R9 is 48. R10 is 128. Addition takes us to 170. Subtraction takes us to FFFFF20. So I had solved all these values in the previous section, and now after I execute SBS I will stay in the same line. This is how we do the programming for direct addressing addition and subtraction, indirect addressing addition and subtraction, and barrel shifter based addition and subtraction. I hope the results are clear to you. All the values from R1 to R12 has been updated by us because of our programming. Thank you for watching.